Consider the standardizing formula for the sampling distribution developed in the discussion of the central limit theorem. Z is equal to x bar minus mu sub x bar divided by sigma sub x bar. We know that it's the standard deviation of the sampling distribution's mean from the central limit theorem. We divided it by the standard deviation here. We can rewrite that. We've got x bar minus mu divided by sigma over the square root of n. Okay? So we've simply substituted in these values here. Okay? This is the formula we know, sigma sub x bar, sort of, and n, the sample size. We do not know mu or z. We can solve for either one of these in terms of the other. Solving for mu in terms of z will give us this. We have mu is equal to x bar plus or minus z, and I'm going to put an alpha in here, times sigma over the square root of n. Okay? This is the formula for a confidence interval for the mean of a population. This will tell us the range in which the true population mean can be found, given a particular probability we choose. Notice that z alpha, okay, has been substituted for z1 in the original equation. Okay? This is where the choice must be made by the statistician. Z alpha is the number of standard deviations lying from the mean of a certain probability. That's what this says up here. This is the number of standard deviations that x bar is away from the mean. When it's down here, it's the true population mean. Okay? If we set the value to 1.64, then we're saying that this is a 90% confidence. If we set the value of z at 1.96, then we're saying it's a 95% confidence. These numbers can be verified by consulting the standard normal table. Divide either 0.95 or 0.9 in half and find the probability inside the body of the table. Then read to the top and the left margins, and you will find those values 1.64 and the value 1.96. In reality, we can set whatever level of confidence we desire simply by changing the z alpha in our formula here. Okay? Common convention in economics and most social sciences sets confidence levels at either 90, 95, or 99%. Levels less than 90% are considered of little value. The level of confidence of a particular interval estimate is determined by the formula 1 minus alpha. A good way to see the development of a confidence interval is to graphically depict the solution to the problem requesting the confidence interval. This is presented in the figure for the case of a 90% confidence interval. But other levels of confidence could have been just as easily have chosen. However, the level of confidence must be preset and not subject to revisions as a result of the calculations. The best way to see the relationships that we've learned and how they create a confidence interval is by looking at these graphs. Let's begin here at the beginning. These are the individual x's, the population distribution. This can look like any old goofy thing. This is the population distribution. Now, the central limit theorem tells us that the sampling distribution of the population is normally distributed. So here's the true population mean, which of course we'll never know. Here's the true population standard deviation, which of course we will never know. Okay? But we do know that the distribution of sample means, these are x bars on this axis here, is normally distributed. Therefore, when I pull out an individual x bar, I know that it came from a normal distribution, this one here, which the central limit theorem, in its kindness, gives us the standard deviation, sigma sub x bar, which is equal to sigma over the square root of n. The mean of this thing, mean of means if you will, is mu sub x bar. Now, what happens? We pull down a particular sample and we get an x bar. That one, let's say, is here, x bar 1, a particular one. What we're doing with a confidence interval is this. We know that this x bar came from a normal distribution. So we draw a normal distribution looks something like this, and a normal distribution like something like that. And this thing here is our old friend z. This is what we came over here. Z is equal to x bar minus mu sub x bar, this guy here, divided by the standard deviation. Because the expected value of mu sub x bar is mu, I can do that. And now I can transform the equation, looks like that. And all we're going to do is we're going to put an interval around the mu sub x bar. This is going to be the confidence level between here and here, which is called 1 minus alpha. We take half the alpha and put it over here, half the alpha and we put it over here, and we find our confidence level by putting, this is 0. If this is, let's say, 90%, 0.90, we call that a 90% confidence interval. Therefore, half of it's over here, 0.5, not 0.5, 0.05. And we got another 0.05 over here. And this number here is 1.64. This is minus 1.64 here. We look these up in our T table, or our Z tables. Okay? We put that in here. Notice what I've done. I've managed to, in this particular case, capture the true mean. But there's no reason that I know that. I will never know that. This x bar could have come from who knows where up here. If it comes from way out here, then I don't capture the true mean. In this example, the true population mean falls within the range of the 90% confidence level. There is nothing, absolutely nothing, to guarantee that this will happen. Further, if the true mean falls outside of the value, then we won't even know that that happened. We must always remember that we will never know the true mean. Statistics simply allows us, with a given level of probability or confidence, to say that the true mean is within the range calculated. This is what was called, in the very introduction to this class, the level of ignorance admitted. Another way to approach confidence intervals is through the use of something called error bound. The error bound gets its name from the recognition that the formula here is x bar plus or minus something. Okay? And that something is called the error bound. And it's the probability we desire to maintain in our estimate created by the z alpha times the standard deviation. Okay? The error bound for the mean is given a name error bound mean, or EBM. Regardless of which way we wish to approach the confidence interval, we now have the valuable statistical tool of a confidence interval. We can say with a known probability what the true population mean value is based upon a sample of data. This is truly inferential statistics.